In this video, we will be talking about conservation of energy. We have a question here, and it says we have a roller coaster train that has reached the top of the first hill at a height of 50 meters. So we're actually right here, and that's the roller coaster car, that's me. Uh, how fast is the train going at the second hill? So when I'm here in this situation, how fast am I going? Um, at the second hill, it tells us that our height is at 34 meters. So in order to answer this question, we need to discuss a little bit about what conservation of energy means. So we're going to take some time to talk about this. We're going to talk about conservation of energy. Conservation energy is a rule that we need to keep in mind, and the rule states that energy is not created nor destroyed. It's just transformed from one form of energy to another form of energy. The energy is always there. It's never created nor destroyed. We can only be able to harness it in one form, or we can transition it to another form and back. So here's what that means. First of all, let's talk about the energies that are involved. There are two forms of energy that we need to be familiar with. The two forms of energy are potential energy. That's the symbol for potential energy. Potential energy, and we're going to call this potential energy due to the height. There is another form of potential energy, which is potential energy of springs, which we'll talk about in another video. But for this video, we're going to talk about the potential energy of the height. And then there's another form of potential energy that we will call kinetic energy, Ke. We'll start with potential energy first. Potential energy is known as stored energy. So I'm going to write that here in our little notes section here. Potential energy is all about stored energy. So what do we mean by stored energy? Well, stored energy is basically simply energy that has been stored, has been built up, because it has the at the end it will have the potential, hence the word potential. It has the potential of transforming into another form of energy. So just know that potential energy is all about stored energy. We can store that energy, in this situation, we can store that energy in terms of height. So basically, the higher you go, the faster you're eventually going to go at the bottom of the hill. So just by increasing the height, you actually store up more and more potential energy, and eventually that's going to give you a really, really fast velocity at the bottom of the first hill. Now, potential energy has an equation of its own. You might want to know this. In order to solve potential energy, you need to have the object's mass, gravity, and height. Keep in mind that height and potential energy are proportionally related. If height increases, so does the potential energy, and vice versa. Now, kinetic energy has its own equation as well. The definition of what kinetic energy is all about motion. So let me write that down really quick. Kinetic energy is energy in motion. So if you're moving, you have what we call kinetic energy. So because of that, we do need to talk about the equation for this. So kinetic energy has an equation of its own, and it's defined as 1/2 times mass times velocity squared. So half times the object's mass and velocity squared. Many students don't like to see it as fractions, so what you can do is you can just take that 1/2, just say 0.5 mass times velocity squared. That's okay. I actually like to write it like this. I like to say it as mass times velocity mass times velocity squared over 2. That way it's easier to move stuff around if I had to do some algebraic rearranging. Okay, so that's what kinetic energy is. Now, let's look at these two situations here. I'm going to label this situation 1, where the object, or where the roller coaster car is on the top of the hill. And then we'll call this situation 2, where the train, the object, is on the bottom of the second hill. Whatever energy you store up here, that's how fast I'm going to be going down here. And so at the top of this hill, the only energy that's happening at that point is just potential energy. We're going to say for this roller coaster that the roller coaster train, is not moving on the top of the first hill. If you've ridden any roller coasters before, you'll notice that some of them that you ride on, some roller coasters actually stop you over the first hill just to kind of build up the suspense, and then eventually, without warning, it'll let you go, and then you actually travel down the first hill. Okay, so at the beginning, at the top of the first hill, it's not moving. However, it does have some form of height. So we can say that the only energy that exists on top of this first hill is potential energy. That's the only energy that exists on the top of the first hill. We can say that 100% of the energy, which we'll call mechanical energy. Mechanical energy is the entire energy altogether. We call that mechanical energy. We can say 100% of all that energy, all that mechanical energy, is focused on the form of potential energy. Okay? Now, when we go down and we reach the second hill, you'll notice that we start to make a transition from potential energy to kinetic energy. And so that's where we're starting to see this transitioning period going on. We're starting to, as the roller coaster car starts to go down the first hill, we start to decrease on our height. And if you decrease on the height, you decrease on the potential energy. So we start to see a loss of potential energy. But at the same time, you'll notice that the object is starting to gain speed. And when you gain speed, you gain kinetic energy. Notice that the speed and the kinetic energy are also proportionally related, but by a value of squared. In other words, there is a direct proportionality between kinetic energy and velocity, but velocity, if I increase by just like double the velocity, that actually increases my kinetic energy fourfold. So there is a significant exponential increase if I increase on the velocity. Okay, so just know that as I increase in velocity, I also increase on the kinetic energy, but by a very, very significant amount. Okay, when we're down here on the second hill, we are now at ground level, which means that there is no height. So we've basically expended all of that potential energy, and all that energy has shifted into the form of kinetic energy. So now down here, the only energy we have is kinetic energy. All of that mechanical energy that was in the form of potential on the first hill has fully shifted, and now you could say all 100% of that energy has shifted to kinetic energy at the bottom of the first hill. Okay, so why am I telling you this? Well, we can say that the potential energy in situation 1 is equivalent to the kinetic energy down here, which is situation 2. So we can say, whatever energy we store up here, that's exactly how much motion energy we're going to get down there. So we can say that the two are equal to each other. Now, as we go up the second hill, you'll notice that we will start to decrease in our velocity. So we start to notice a decrease in the kinetic energy. Or, I'm sorry, a decrease. But not fully, because you'll notice that as we go to the top of the second hill, we don't totally lose all of that motion. It's actually still moving over the second hill. Otherwise, we won't be able to make it over the second hill. So there is some form of speed left on the top of the second hill. So we do still have a little portion of kinetic energy left. We can say that we have about, I don't know, let's say we have about a good 30% of kinetic energy left. But the rest of that energy has been transferred to potential energy, because at the same time, we also have a height. So we can say that the rest of the energy, the rest of the 70% of that energy, that mechanical energy, is shifted to potential energy. So you'll notice that there is a portioned out perspective or view of the mechanical energy, the total energy that's happening. You can say that 100% of all the energy at the bottom of the second or of the first hill, all of that energy is kinetic. But then as we go up the second hill, 70% went to potential, the other 30% is still kinetic. So you can say that the kinetic energy, the collective mechanical total energy of that's kinetic energy on the bottom of the first hill, we can say that that is equivalent to the combination of the potential energy and the kinetic energy of situation 3. Situation 3 is where the car is at the top of the second hill. And so we'll label this as potential energy due to the third situation and the kinetic energy due to the third situation. And so we can say that this is equal to the kinetic energy that we have at the bottom of the hill, which is equal to the potential energy that we have on the top of the first hill. That we're kind of seeing a trend here. If this is equal to this, and this is equal to this, then we can say that the potential energy that we store initially on the first hill is going to be eventually equal to the combined potential and kinetic energy over at the second hill, here on situation 3. And so basically, conservation of energy is telling us that all three situations are equal to each other. All the energy that was stored up on the first hill equals all the energy that we're ever going to get down the second hill when it's all in motion. But then after that, as we go up the second hill, a portion of that energy went to potential energy because it's starting to gain height. But then we still have a little bit of kinetic energy left because it is moving over the second hill. And all of that energies combined was what energy we had on the first two situations here in situation 2 and here in situation 1. So now we can just say that everything here is equal. So just as a recap, you might want to first of all label all of the energies that are happening in whatever situation we're looking at. The key thing to remember is if there's height, you have potential energy. If it is moving down here, you have kinetic energy. And if you're up here on the third situation where you have a combination of both the height and it's also moving over the hill, then you have literally a combination of both as signified here. And then you can just say that all three situations are equal to each other. That's how to work out the concept and the math behind the conservation of energy. Okay, let me go ahead and clean this up a little bit so that way you can kind of see the diagram a little bit better, and then we're going to go ahead and do some math. Okay, so here's how it looks like. Again, remember, label all the energies that you see in each of the situations, and then just make sure that they're all equal to each other. The next thing I'm going to do is I'm going to make sure that each of these energies are enclosed in brackets. I want to make sure that everything is treated, all the energies are treated as one unit. Because like you saw earlier, each energy has its own equation. So you want to make sure that it's all organized and that it doesn't mess you up when you're trying to do the math. Now, all we know are the heights for the potential energy on situation 1 and the potential energy and kinetic energy of situation 3. We don't know anything about the velocity over in situation 2. We don't know how fast or how much kinetic energy this car has at the bottom of the first hill. However, if you just look at the math, because this is equal to this, and this is equal to the combined energies of that and that, then you can eventually say that this is also equal to this. So we can just take this part of the equation out. And so if we do that, we get this. Okay. Once we're here, we can go ahead and substitute each of the energies for the equations that they stand for. So the potential energy on situation 1, which is up here, can actually be broken down to mass times gravity times height. And I'll keep those in brackets because I do want to treat them as one number. The potential energy on situation 3, that's right when it's up here on the second hill, that is mass times gravity times height again. But again, that's the potential energy over at that second hill. So I'm just going to say this. Okay. Just keep in mind, the reason why I have these Roman numerals is to say that this potential energy is totally different from that potential energy. In other words, this potential energy here is totally different from that potential energy there. Okay, that's why I have those Roman numerals there, so that way you won't get confused. All right, let's go ahead and break down the kinetic energy. So for that one, we get mv squared over 2. I'm actually going to write velocity squared in a different color because we're actually asked to solve for that. So we're going to say velocity squared over 2, just like that. And this is for situation 3, where the train is on the second hill, which is this one right here. So this is situation 3. Okay, let's go ahead and plug in, or actually before I plug in the values, you'll notice that algebraically the masses can cancel out. So there's no need to know the mass at all when you're dealing with a conservation of energy question. We basically took the equation and simplified it. So now we get something like this. All right, so now we have this. Let's go ahead and plug in our values. I don't like to move the equation around until I can actually get one number for that part and one number for that part. So let me just go ahead and plug in our values. So the gravity, or actually, I'm sorry, the height of the first hill is 50 meters. So I'm just going to go ahead and write that down here. So we're going to say gravity, which is 9.80, and our height is 50 meters. And then we're asked to break this down. So the gravity and height of situation 3, so I'm going up here, here's situation 3, the height is 34 meters. So I'm just going to plug that in. So the gravity again is 9.80 times 34 meters. Plus velocity squared over 2. Oops, wrong color. There we go. And once you're here, you can actually go ahead and multiply these numbers together. So I'm going to multiply that, get one number for that, and then we'll multiply this and get one number for that. So let me go ahead and just put that in for you really quick. So these are the numbers that I got. Now you can actually go ahead and rearrange the equation because it's as simple as we can get it. So I'm going to go ahead and subtract 333.2 on both sides. And so that cancels out. And now if we just subtract that, 156.8. That is equivalent to velocity squared over 2, which at this point we can go ahead and multiply 2 on both sides. We're just going to go ahead and isolate our v squared. So we do that and multiply those two together. We get 313.6. And keep in mind that that's actually velocity squared. So we need to take out the square by doing the square root of that number. So that will cancel out. And so now our new answer is 17.71. And so that is the speed. Oh, let me put down the units as well. So velocity or speed is meters per second. So this is how fast the roller coaster is moving on the second hill, the top of the second hill. We can say that the roller coaster car is moving at a rate of, so our velocity now is 17.71 meters per second. And that's our answer.